So hi, everyone. Hi, I'm Jacqueline Nolis. This talk, From Laptop to Cluster, Moving from Local Environments to Dask and the Cloud, was made by a senior data scientist, Nathan Valu, who is going to be presenting it. But unfortunately, he had a sudden emergency. And so I, the understudy, will be presenting it instead. I also know a thing or two about Dask. So you'll still get your money's worth, but that is just the last minute change in the program. And thank you all for joining. So today we're going to be talking about really how do you go from just doing data science on your laptop to, okay, I now want to use a cluster of computers. So before we talk about that, there's also the earlier question of like, when do we even just move off your laptop at all, right? I was a data scientist. I worked for many years, most years, just as a person who did all my data science on my laptop. I had R or Python installed on the laptop. It had a fixed amount of RAM. It had a fixed amount of hard drive. And that was fine. I just used it and I made it work. But eventually, I did start to run into occasional problems where I'd be out of memory. I would need more processors, things like that. And it was just a struggle. So moving to the cloud would have solved that because I could have used whatever size computer I wanted by just renting it in the cloud. It also had problems when I was working with the team. There'd be problems because I would be doing some work on my laptop and it'd be hard to share it with someone else because it's all locked into my laptop, how I installed it. I'm blurry. Here we go. Am I blurry? There we go. And there's some reproducibility problems because hey, if I drop my laptop in a puddle, it's game over. I mean, even with Git, still knowing what libraries are installed, things like that, that's all a problem. So moving to the cloud can be really advantageous. It is even more advantageous to be able to move to the cloud and use multiple computers at once, which is to say, there are times that I'm on my laptop and I'll run something in parallel. I'll want to run something in parallel, like have a couple different computations running. It would be super cool if I could have those computations running on entire separate machines. And it'd be cool if I didn't have to go out to Best Buy and buy new machines, but I could just use the cloud to get a bunch of machines to run concurrently. If you imagine, when you think about running a lot of stuff in the cloud, you could spin up a ton of virtual machines yourself, install Python on each of them, run some stuff, or you could use some sort of system that will connect all of these things for you. So you can just say, run my code, and it will execute across the cluster. And if you do that, you get all the benefits from before, but you also get near infinite amount of scale because you can always add more computers to however big your cluster is. So there's a real advantage to being able to, when you feel like it, use a cluster of computers in the cloud, which is why you're presumably watching this presentation. So to do that, we're going to talk about a library called Dask. So Dask is one of several libraries in the world that lets you do distributed computing. Another very common one is Spark, right? You may have heard of Spark as a way of getting your data science computing to happen on a big set of computers at once. Spark has the problem that, I think it's a problem that it runs in Scala, which is based on the JVM. So you're talking Java and stuff, which makes it sometimes hard to use Python or other languages with it because you have to have a whole interface to get it converted to Scala and run that way. And there's just a lot of layers that can get disconnected. Dask is a Python library. So when you're using Python, you can just have your Python code run across a bunch of other computers. And it's a lot smoother because you don't have to worry about converting languages, things like that. You can take a Python function and take that function and then tell it to run on any number of other computers. And so this really opens up two things. One, you can distribute parallel calculations. If you have, let's say you have a data set and you want to train 10 different models on it, you can train all those models all at once. You can train one on each machine. It also allows you to distribute a large data set. So let's say you have a 100 terabyte data set and you really want to do an analysis on all of it. So you need it all in memory. Well, you can split that data across a bunch of different computers, just chunk it up small, do small analyses on those chunks, and then bring it all back together. So those are really kind of two fairly different uses of Dask, either distributing a bunch of calculations or distributing data across a bunch of things, calculating on that and bringing it back. And Dask is pretty good at both of those. So let's talk a little bit more about how Dask works and what is Dask. Wait, I pressed the wrong direction. There we go. Okay, here we go. So see, I'm the understudy, so I'm new at things like pressing arrows on keyboards and stuff. But okay, so the Dask architecture works something like this. You have the client that you're code is running on. And so this is like the laptop or something. Like this is the core place where you hit run on your code and it does stuff. That's the client. That's like the place where all the important like code running, code is actually happening. What the client does with Dask is the client will, when you use a Dask command on the client, it will then pass it to a scheduler. The scheduler will then take those commands or tasks, take those tasks to do, and it will distribute them among a bunch of workers. So those workers are like what you think of your distributed cluster. There's lots of computers actually doing all the math. And they can talk to each other. They can talk back to the scheduler. And then that goes back to your client. So if you want to do a calculation and you want to do a parallel calculation, like run 100 things concurrently, you will send that to the scheduler. The scheduler will start passing around to the workers. The workers will do their computations. The scheduler will take all the results, aggregate it, and then pass it back to the client. This is important for a couple of reasons. One, that does mean your scheduler is important in that if your scheduler is really small, a really small computer that doesn't have much memory, then you're going to be limited because the client has to pass everything through the scheduler. So you actually have to think a little bit about the size of your scheduler. And two, it also means the size of your worker and the number of workers can affect things. So you can imagine the performance of your Dask cluster is going to be really different based on whether or not you have 100 small machines, all as workers, or 5 big machines, all as workers. And especially each worker machine could itself be doing parallel calculations on it. This is just to say that while you may have this core architecture of a client connecting to a server, connected to a lot of workers, there are hundreds, thousands, an infinite number of ways you could actually utilize this amongst a bunch of workers. So, okay, so you have your client and you're telling it things like, hey, I want to take these 1,000, I want to take this function, I want to run it 1,000 times in parallel, and then take the result and do something with it, and then take the result, do something like that. When you are making these chains of take this result and pass it to this function, and then take that function, do something on it, you're creating a sequence of tasks. And Dask will create something called a task graph based on that. So the point of the scheduler is it actually keeps track of all these different tasks, and it's going to be clever about telling which worker to do what. So if you have a task that, you have a task that requires 2 other tasks to be done before you run it, the scheduler is going to realize, okay, don't ask a worker to do that task because we're still waiting for the previous ones to be done. That big thing is called the task graph. Here's an example picture of what a task graph might look like. Actually, Dask has some very easy visualization. So if you have a Dask cluster and a set of work you want to do, you can always hit task, you can always tell it to visualize the graph and you can actually see for yourself what the thing looks like. And so this task graph is constantly getting changed. If you're passing more commands to it, it's going to be adding more and getting bigger. And then as those commands are getting completed, it's going to get smaller. So it's like a continuously updating thing. And so like as a very concrete example of a task graph, if you're doing a model training, you may at the start be loading data, and then that data needs to be passed to clean the data, and that data needs to be turned into features, and then another data set has to be loaded as well, and a similar thing happens, and they take those features and you pass it all to a model. When the model is changed, it made a prediction. Like you'll have these big sequence, and Dask is smart enough to know when you're distributing this work out to your workers, it's smart enough to know to do it in a good order where you do the earlier ones first and wait on the later ones. And so this is just a nice thing because like for me personally, when I think of running things in parallel and over distributed cluster, I always assume I have to have like 1,000 tasks that all run concurrently and then finish, and then like 200 tasks that run after that with all the results. But like you can actually have a much more complicated thing where like some things are done and some things are in progress and then they still are known to be fed into the next thing. So like your task graphs can get fairly complicated and the cluster can handle that for you, which is pretty cool. Okay, so that was a lot of talk, but I haven't actually told you like, how would you use Dask? Like, how does it actually work? Like, what does the Python code look like to use Dask? So there are a couple core ways you can use Dask. The first and perhaps most popular is, actually, I have no idea if it's most popular, but it's very cool and people talk about it a lot. So I like talking about it first, are Dask collections. So a Dask collection is basically the idea of like, hey, we know you. You don't want to have to think about parallel stuff, do you? You don't want to have to rewrite half of your code base so that instead of running on one computer on your laptop, now your code base can run in a distributed cluster. You really don't want to have to rewrite everything. So what if we did the hard part for you? And we made it so instead of using like a data frame and pandas on your laptop, you're going to feel like you're using a pandas data frame. But instead of using a pandas data frame, it's actually a whole bunch of tiny pandas data frames distributed amongst the cluster, but you're still interacting it with the same way. So that's the idea of a Dask collection is, hey, we're going to make it so you don't have to worry about parallelization. Like really try not to think about it. Instead, just think about doing the stuff you know and love, and then we'll handle the parallelization on the back end for you. So they're really trying to mimic existing data types. So like a Dask data frame, the idea is it mimics a pandas data frame. So I have some code here down on the bottom left. So on the top, this is what you would do in pandas. So you read the CSV, you could like do a group by and then a column and then do mean. If you were using Dask, you would import Dask data frame instead. You'd use the same read CSV command, the same group by, the same mean. The only thing that would really change here is that the compute call is added, which just tells Dask to be like, okay, actually go run this. And so this is nice because your code barely changed and the way you reason about it didn't really have to change. But now that instead of a pandas data frame being stored in memory on one computer, your pandas data frame is stored, or that data is stored in like 20 pandas data frames, all passed amongst a bunch of Dask workers. So for you, it feels the same, but actually things can run much faster in parallel. So Dask data frames mimic pandas data frames, Dask array mimic NumPy arrays. There's also Dask bags, which kind of just mimic like lists with map and filtering. And so all of these are ways to be like, I want the benefits of parallelization, but I don't want to have to really think about parallelization. What can you do for me, Dask? I have a little asterisks here because it's like, well, you get all the benefits for free. Like we'll get back. There are occasionally troubles, but in general, you're mostly fine just thinking about things in a non-parallel way. So another cool way you can actually use Dask is with Dask Delayed. And so with Dask Delayed, you are much more explicitly stating what the tasks are that you want to have Dask do. So whereas the data frames and the collections are like, hey, I don't want to think about parallelization, you deal with it, Dask. Delayed is like, no, I very explicitly want to tell you all the different things you have to do. And then I want to hand those to you, scheduler, and then you figure out how to allocate them. And so Dask Delayed, what you're doing is you're taking functions you would have in base Python, like you would normally write in regular Python, and you add a @Dask Delayed tag or a decorator to the top. And when you add that, what you are then saying is, hey, when this function runs, I actually want it to be handled by the Dask scheduler, which will then farm it out as appropriate and then return the results. And so this is lazy, meaning it won't actually run until it needs to. So if you look here, I defined a double and an add function. And so here I said A is equal to double3, B is double2. Total is adding those two together. So as of this line, nothing has run yet because it's lazy. Since I haven't like asked to use total yet, it's just waiting. But if you'll notice, this is also actually a task based on other tasks. So the add function is pulling in data from the double functions. And like this is creating a small task graph. And so if and when I hit .compute, the scheduler will pass these three tasks out to the workers, and maybe a different worker will be asked to double the number 3, and a different worker will be asked to double number 2, and a third worker will then take the two results and then combine it back together. Like Dask will figure out all the exact implementation of that out for me, but I will be telling Dask what are the particular tasks I want it to do. Here I've used Dask @Dask.delayed to decorate them. You can also like actually use the function Dask.delayed and put the sub function inside. Like there are a couple of different ways you can actually define this, but the core idea is just, hey, I want to be creating these little functional blocks, and then Dask, I want you to be able to schedule it, which is again pretty useful. For me, and then there's this last one, Dask futures. And for me, this is, I kind of think about this in a different way as Dask Delayed. Whereas Dask Delayed is very much like, I want to be creating tasks and I want to pass these tasks to the scheduler that's going to efficiently allocate them. Dask futures, it is basically a port of the Python-based concurrent futures, which runs things in parallel, which this one I actually find pretty practical for me as a data scientist. Because Dask futures, the way it works is you may have like, you can pass it basically, like it's not lazy. You like pass it, okay, run all these things at the same time, and it will do that. So if you have like, 1,000 different data sets and you want to train a model separately on each of those data sets, you can be like, Dask futures, do all these in parallel right now, and it will take it and run with it. So some example code down here at the bottom, again, if I had that double function, I could just do submit on a single thing. And that's saying, Dask, go run this right now in the cluster, just this one thing, in which case it's not particularly thrilling, but I could pass one command. Or I could pass, like here, double, I can use .map, and then I'm going to use that same double function. And maybe I want to run double on all of these. And so this is very good if you have like, I want to train model on 1,000 different data sets. This client.map will say, okay, go right now and train all those models. And And so then you can use gather and futures. Basically, futures will be running in the background because the cluster is running on the background. So you can choose to either have your client be doing other stuff while it's running, or you can use this like gather and compute to wait until it's like, okay, once I've gotten the results of all those 1,000 model trainings, then let's move on to the next step. So this, to me, this is kind of more how I traditionally think about running things in parallel, of like very much, I just like, okay, go right now and run all these tasks. And so futures is kind of a nice way to just do that. So as you're starting to use these calls, these futures, these delays, the collections, you may be running into situations where it's like, this is going really fast. This is going really slow. I would like to know what is going on in the back end. And so with Dask, Dask also has some built-in dashboarding, which is just really nice to try and debug, and give you an understanding of what's really going on. So there's a couple of different like views built into the dashboard of Dask. And, there's a couple of different ways you can view the dashboard. You can use the task stream where each one of these bars is a worker, and you can look at like the colors and tell like, well, what is it working on? Is it waiting? Did it have an error? You can show the progress to be like, okay, given a particular task, how long is that task taking? What's holding it up? You can also look at like the actual worker utilization. So if you have 1,000 workers and none of them are being utilized, you'd be like, maybe I didn't need a cluster for this. Or if you have 1,000 workers and they're all being utilized at 100%, it's like, maybe I should have 2,000 workers. So the point is you can use these kind of dashboards as well, that as you start using these Dask functions, you can kind of be debugging, well, is this working in parallel the way I would have expected it to? So everything I talked about so far was just purely about Dask itself. But at some point, you're like, I would love to actually use Dask on a cluster in the cloud. That feels like a hassle to set up. How can I near immediately just have a cluster of computers available for Dask? Saturn Cloud provides that as a service. So in Saturn Cloud, we have these Jupyter resources, which are just like computing machines you can turn on, you can run your code on, you turn them off. You can also then attach them a Dask cluster. And so in the UI, you'll see this like Dask cluster button next to your Jupyter server. And what you can do is you can say, hey, I would like a cluster of this particular size with this number of workers, and each worker has this much memory, blah, 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 and then hit start on that. And so from there, once these things are both started, any of your Dask code in Saturn will then be using that cluster. And so in this case, you do like from Dask Saturn, import Saturn cluster, and then it would just make the connection to the Dask cluster. You could have just as easily, if maybe not just as easily, but you could have also, if you wanted to, have set up the entire Dask cluster yourself on Kubernetes. You could have set up, there are other services as well that you can use Dask. You can also even use Dask from within your local machine. So if you're like, I really do want a cluster of processes running, but I don't want them to all be on a separate machine. I want them like to have like little tiny ones on the same machine. That kind of work as well. So there's a lot of ways you can use Dask, but we've made it pretty easy that if you want to just get a cloud resource running that has Dask on it, you can just spin it up in our user interface. So now we're going to pop into an example. So hold on. So we're going to pop into an example real quick. And I foolishly closed the tab. So give me 1 second as I get this set up for you. So here is an example of using, actually, I'll go back to. So when I'm in Saturn Cloud, I have a resource running this laptop to cluster example. So this is the example of the resource. The Jupyter server is running, the Dask cluster is running. It's got some workers, each with 4 cores. And so I can hit Dask dashboard. Oh my God, Dask dashboard to get that dashboard I was talking about, or I can hit Jupyter Lab and that'll pop me up into Jupyter Lab. And so in Jupyter Lab, I have a couple different, just like, look, here's some task in practice for you. And let me make my screen bigger because I know my screen's pretty large, so I want that to be visible. Great. Okay. And then, so here's an example of how you'd use Dask to distribute data. So in this particular example, I import Dask DataFrame instead of Pandas. I have some like helper stuff, but really I'm just using Saturn cluster. I'm then starting the cluster, or I'm connecting to the cluster, and I'm also using a wait for workers command. And that wait for workers just says, hey, if the workers aren't done spinning up yet, let's wait for them to be done spinning up. And so then just like Pandas, I can read in the Parquet and save that into a Dask data frame instead of a Pandas data frame. So here I'm reading a data set of stock data, I can tell my code, hey, wait till that, because again, Dask is lazy, so that data won't actually be loaded yet. It'll just, Dask will be using it as a placeholder. So I can use persist to be like, okay, no, actually load it and then wait. And this, or sorry, the persist means load it, and then the wait means like actually wait till it's loaded to move on. And then I can just do some simple pandas commands, just like I would in pandas, but I can use them in Dask DataFrame to do some sort of calculations I'd want and get the total. And so this is all lazy. So none of these commands actually happen yet up until I do this .tail, and that actually will go and collect it and bring it back to the client machine. And so you can use this to get all of your data. So the point is, like, when you look at this code, it doesn't look like wildly different in parallel. You're still primarily reasoning in kind of a panda style way, but you're using stuff in parallel in the cloud. So that's for if you wanted to like distribute data amongst a bunch of workers and then like do calculations. You could also distribute the calculations themselves. And so this is an example of hyperparameter tuning a PyTorch model. So if you imagine if I have a PyTorch model and I want to run it with a bunch of different parameters and see what works best. So, I loaded my torch, I loaded my pandas, or my Dask, things like that. Again, I start up the cluster. Here it's a cluster where each resource has a GPU on it. Like, that's totally fine. As long as it works in Python, it'll work in Dask, and GPU stuff, you can use Python for. So then we upload some files to each of the workers. And we actually here define a model, a function that trains a model. So this here is just plain Jane PyTorch, which is I'm going to pass it a learning rate, and then I'm going to train a model based on it. But I add this Dask Delayed decorator. And then here at the bottom, I can actually run using futures. I can say, okay, run using a couple different learning rates, actually pass them all concurrently to that training model, and like run whatever number of versions of that training that model on each of the different learning rates, and then compute the results. There are ways to handle errors too. So there's like a lot you can do, but the core idea, like, you don't have to totally rewrite your code for parallel. You're primarily thinking writing PyTorch stuff, and you're just saying, hey, run this in parallel for me. And then I'm going to figure out, where did the window go? Okay, here we go. So then we're going to keep going. Here we go. So that's the basics of Dask. So now let's talk about a lot of the fussier stuff, because you're like maybe watching this like, okay, I'm convinced this kind of seems like a cool tool or things like that. But like, surely there are things I'm going to have to run into that are more complicated than what you just showed me in the demo. And it's like, yeah, okay, sure. So a couple of fussier things. So first off, as I said, you can use a Jupyter server in Saturn Cloud to just pretty quickly connect to Dask, but you can be like, 1, I don't want to use Jupyter. 2, I don't even want to use your computer at all. Like, all I want is that Dask cluster. Nothing else matters to me. So the canonical method in Saturn Cloud is you spin up a Jupyter server, run Jupyter Lab in there, and use notebooks to connect to Dask cluster. You could also just as easily be like, hey, if you're using Saturn Cloud and you don't want to use Jupyter Lab and notebooks, you could just SSH into that client machine, into the Jupyter server. And so in that point, you're no longer using Jupyter Lab, you're using whatever you're doing on your SSH machine, and then you're using that to connect. But in this case, you have 3 computers. The laptop you're connecting with via SSH, that connects to the Jupyter server and then the Dask cluster. Or if you want in Saturn Cloud, you can directly use a laptop and stuff and then use a cluster in the cloud, which is to say, more broadly, if you have a distributed computing cluster in the cloud, you have really 2 different ways you can use it. You can either also have a client computer in the cloud that accesses those, or you could use your laptop and you can have your laptop access the cloud cluster. There's kind of advantages and disadvantages to each. The advantage of having everything in the cloud is it's just all the benefits of the cloud. It's in a shared place. But again, like, we all love running from our laptops, right? So if you have a particular reason that you want to do that, you can just have your laptop connect directly to the Dask cluster as well. So another question is, okay, so you're using Dask and you have all these like client computers running in a distributed, sorry, you have all these workers in a distributed cluster running in the cloud. And you're like, oh man, I would love to use some particular Python libraries and packages like PyTorch or things like that. And I want to use them on the Dask cluster. How do I actually get those set up? Well, if you use Saturn, when we use those Jupyter servers, whatever packages and stuff you have installed on the Jupyter server, we just make sure it is installed on the Dask cluster as well. So any particular Python libraries or things like that. If you are not using Saturn Cloud, you do generally then have to do the work yourself of making sure whatever your client computer is running is also using the same packages and software as your Dask cluster. So it is just a matter of setting up Python libraries in 2 locations, but you will want to take care to make sure that you're not using different versions of Dask, or like the Pandas version on your laptop is different than the Pandas version in the cloud, all that. So it's just like a kind of thing you're going to want to be careful about, because that is an unfortunate catch where you're trying to debug an error in your Dask cluster. And you're like, why is this code not working? And it's like, because there's an inconsistency in the libraries you're using and it's not running how you'd expect it. So just to add another complexity to this, if you are like, let's say you are, you have like a module that you want to use, and like maybe you're adding that module on the fly on your client, right? So like you have this like helper function module, and you really want that helper function module to also exist on the Dask cluster. And like in real time, you want to be able to make sure these things are synced. So Dask has some functions that you can use to do this. Basically, there are a couple ways you can do this. One is you can use like a worker plugin, and a worker plugin will allow you to sync the stuff you have on the client with what you have on the Dask workers. So you can kind of keep it constantly synced. So as you make changes to files on your client, then they will be properly passed to the Dask workers. Or Dask has built in a upload file function, which will upload an individual file to all of your Dask workers. So if you have just like one file of like helper functions, or like some special thing that you want to get on your Dask workers, you can manually use the client functions to upload them to the Dask workers. That said, this is just more broadly, this is a thing you will again have to think about. Whereas before, when you're doing local work, you can just be like, well, everything is always local, so I always know exactly what I'm going to get. Here you are going to have to put a little more thought into like, well, what functions, what code, what packages are actually available on the workers. Otherwise, you're going to run into some issues. So another thing that you'll want to think about when you're using Dask workers is, okay, so you're using a cluster, it's going well, you're distributing your calculations, but there's some error there, something, and you're like, my code just breaks and I can't tell why. And it's because when you're running local, you can just use prints and error messages, and that all just gets past the console, and that's all pretty good. But when you have like 10 workers, 20 workers, and they're all having their own logging and errors and things like that, you have to actually put thought into how is the messages that are creating on those workers going to get passed back to my client so I see them. So Dask has a logging function. And so the logging function will let you then, when you use the logs there, it will then get passed to your client machine. So for example, on the left, I can show like, here's a function that just sends a log from the worker and in a way that you can capture. And you're just going to have to be careful about that, because that's one of these things that, again, thinking about where the errors getting logged is a thing that's going to get a little trickier when you're doing things distributed compared to when everything is just on your laptop. Another thing, there's a recurring theme here, which is keeping track of stuff between your distributed cluster and your client. So another thing is, when you're doing everything local, you have your hard drive, and everything of your, all of your code can reference your hard drive. But if you're doing things with a distributed cluster, they don't have the ability to just all pull from the same file system directly, because these are all running on different computers. There's really like one core way to solve this, which is you need to make some method of storing files in a way that every one of the Dask workers can get access to them. And imagine if you have like 100 gigabytes of data or something, you're going to want to be really thoughtful. Like you can't just do client.file, upload 100 gigs to each one of those workers. That would be too much. You're going to have to be thoughtful about how you actually pass the data. So here's just a couple examples of ways you could do it. So like one thing that's like kind of straightforward is like just use a cloud file storage system like AWS S3 or BigQuery or whatever you want. Just have, or a SQL table, just have some shared storage location, and then have your Dask workers, when you pass a function, have your Dask workers load up data from those locations. And there are ways to do it where you can tell Dask to like load the data load the data and then keep track of it, so you don't have to constantly be reloading it every time you have a new task. But the point is that only works if you have one cloud shared storage location. So as you move to using a distributed cluster, you're also going to want to move to having a shared storage location that the cluster all has access to, which maybe you already have depending on the data, but sometimes that requires moving stuff from your like laptop hard drive to a cloud location. Just one other method. So Saturn Cloud, because this is such a thing that happens so often, we've built into our product shared folders. So shared folders are a way of just directly attaching like a hard drive to all of the Dask clusters that is shared. So that's specific to Saturn Cloud. But like that is, again, just another way of solving the problem of, hey, I need all of my Dask workers to be able to connect to the same data. So another issue that happens when you move to parallel, and I was kind of saying this before, which is like you might be running some code and it might have an error. And like the nightmare scenario that people talk about with distributed computing and things like this is like you have a massive set of computers, you're running them for hours, you're at like 97% completed with your parallel computations. And then one of them has an error, your code doesn't know how to handle errors, so the whole cluster shuts down, and then your hours of work, your money is all lost. Having that happen is the worst. So ideally, what you want to have happen is you want your code to be able to have an error and then overcome it. So a nice, easy way to do this is with the futures package, that the futures Dask methods, when they run all these things in parallel, they will actually, if there's an error, it will be isolated. So if you have 1,000 computations all running in parallel and one has an error, futures will just be like, okay, here's all the results. This one had an error. And you can, write retry logic, or you can add some sort of logic around that. You also might want to have stuff where like, hey, when your computations are running, if they are very long running computations, like maybe save an intermediate step, like save partial data like in location, so that if your task has to restart, it doesn't have to do all of that again. It can pick up where it left off. That's all pretty valuable. But the core point is you do want to kind of think more about where the errors are happening and think about like using a tool like futures, which does allow you to capture the state of thing. Or if you decide you don't want to use futures, then just really code in the logic of like, have a lot of try catches and things like that in your code so that you can kind of be thoughtful about where the errors happen. And this code here, this actually just shows a particular example of using futures. And in this case, we're like iterating, doing some computation, and we're iterating through. And for everyone that it's fit, anytime a task finishes, we'll like print a message. But if there's an error, we will handle it differently and we'll work with that. And so then my code won't crash. It'll just print the appropriate error messages and I'll move on. Also keep in mind, Dask is fairly thoughtful about like certain types of errors. So like if for some reason like the power went out to one of your workers, or like one of your workers suddenly died, the scheduler is clever enough to notice, hey, that worker was unable to finish its computations. I'm going to spin up a new, I'm going to make another worker kind of handle them. But it's not perfect, right? Like there's like, and if your code is always going to cause the worker to shut down, if it's your code causing the worker to shut down, having that code go to another worker won't necessarily fix it. And if there was data that was only stored on that worker and it went down, like again, that can't be fixed. So the point is, this is just something you will have to think a little bit more about that you don't necessarily have to think about when you're doing stuff locally, but it's probably still worth it in the grand scheme of things, given how much power you can have with parallelization. I feel like a lot of those fussy parts were downers of like, oh, here's hard things you have to handle. Here's a cool thing about Dask, which is machine learning is especially useful and easy to do with Dask. So a lot of packages like XGBoost, Rapids, LightGLM, they are designed so that if you're using Dask and you're using a Dask DataFrame, then they will work with that Dask DataFrame and they will do it in parallel, distributed for you. So a lot of times by using Dask as the backend, you can just purely get a speed boost on your functions. And it's just by running things in the background. So again, you don't have to think about the parallelization yourself. There's also the Dask ML package, and there are other, like even if you don't use a built-in package, you can also just use Dask for the machine learning task of like, hey, I want to farm out a lot of different models to try training for hyperparameter tuning, or like Dask ML does like grid search kind of stuff. Like I think with scikit-learn, so it like can grid search and actually find the parameters better for you. So there's like a lot you can do in that way. And then also, and we'll talk a little bit more about this, but like some machine learning libraries like PyTorch actually let you, like PyTorch is designed for scenarios where you have distributed clusters running all together to train a model, right? When you hear about like Google releases a new model that's trained on, a year's worth of power for an entire town, the way they do it is by using distributed clusters all connected to train a model. Dask is a nice way to have a kind of, like an interface to set one of those up for yourself if need be. Okay, and so then one more thing that can show up is, again, we're having errors in debugging. Sometimes the parallel doesn't necessarily work quite the way you want. Like you're like, hey, I'm using Dask DataFrames and I was expecting to go a lot faster, but it's not going that much faster. And so oftentimes what happens is you get to a scenario where because of your particular way you're trying to slice data and use pandas and things like that, pandas, Dask DataFrame may not end up giving you a direct speed boost. And that's nothing against Dask DataFrames in particular. It is just, in general, there are some tasks that if you try and parallelize them, not only will they not be faster than doing them single threaded, but sometimes they will be slower because you have to be passing information between all of the workers. This happens. And I think Dask DataFrame in particular, this happens with, because the Dask DataFrames are the ones people are most likely to be like, I will just do a 1-for-1 swap with pandas and call it good. But that's fine. Dask has a lot of, if you get to that point where like, well, this isn't working the way I want it to, you can then switch to Dask Delayed, Dask Futures, which have more, fine-tuned control of how things are actually going. And in general, a Dask data frame is just a collection of pandas data frames spread across a bunch of workers. And so sometimes if you just remove the pandas data frame or the Dask data frame and then manually say, okay, I'm going to manually create a bunch of pandas data frames and do the calculations myself and then combine it, you will be doing things in parallel and you will do them because you know how your data works and what you're trying to do. You can do it much more cleverly with Dask than the Dask data frame could directly. And so sometimes it's best to switch to that. So that's all to say that, again, when you start to switch to parallelization, you will have to start thinking about this stuff a little bit about like how much I'm going to use a built-in function versus make my own or things like that. But again, because you can get such a powerful speed boost from doing this, it is often worth it to have it that way. Okay, and so then lastly, I have another case study, which I was kind of just briefly alluding to merely a slide or two ago. And this is one I did with Dask and PyTorch. So this is, okay, so I personally have a neural network model that I love training, and I use it as my test case for all sorts of things. And what it is training a neural network to take a list of pet names from Seattle, like pet license data, take those pet names and train a neural network to generate new pet names that are fake but sound like pet names. And the way that works is with PyTorch, or I also use Keras sometimes. You can actually, I make a neural network with LSTM layers, and then I train it on the data, and then I do that. But sometimes this model takes a while to train, and I'm like, I'm really interested. Can I just take a NLP model I have in PyTorch, and can I train it across, instead of training it on one GPU, can I train it on a bunch of GPUs in parallel, and how would that kind of improve things? And so I just said, okay, let's do this as a case study and see how it comes out. And so what I did for PyTorch, so PyTorch has a built-in, it's called Distributed Data Parallel Library. And again, that's the library that PyTorch uses for, so you want to spend an entire year's worth of energy from a town on training a model. Here's how you distribute it over a cluster. It has that built-in library. So I'm going to be like, well, I'm just going to train the smaller model on just a few workers. And so by doing this, I'm going to be able to use workers, each worker with a GPU. So if I have 3 workers, that gives me 3 GPUs I can connect all together and train a model. And so the basic idea is that how this works in practice is that each one of the different workers in Dask has its own torch model that it's training. And what they do is I'll pass it, each worker, a bit of data, it will train on that. And then all the workers will concurrently readjust based on how all the other ones trained, and they're going to all keep going. And so in essence, I'm actually training 3 models that are all basically the same, but I'm training them all in parallel, and then I'm constantly having them communicate so they all learn from each other. So from a from more of a ML perspective, what I'm doing is I'm simulating having a combined batch size, a model that has a combined batch size of, if I have 3 workers, then 3 times the bigger batch size, because I'm taking one batch, I'm spreading it to 3 workers, they're all training, and then they're all communicating. Or I guess in this picture it was 4 workers, but you get the idea. So if each worker had a batch size of 1,024 that it trained on, they'd each train on 1,024, they'd all communicate, and then I'd basically be training on a batch size of 4,096. And so when I use that with Dask, what I'm doing in practice is each Dask worker is running a model training function. So just like I showed in the first example, where I'm like, hey, I'm going to write some Python code with PyTorch to train a model, I'm going to again do that, where I'm going to have one function that will be to train a model. And that's the same basic function I would use if I was only training on one GPU on one machine. But then what I'm going to do is I'm going to have a DDP call in there. And so the DDP call will, after each like batch, will then say stop and communicate with all the other workers and then keep going. And so at Saturn, we developed a Dask PyTorch DDP library, which is basically, it's like a wrapper around futures to handle this a little bit for you, but you don't need that. That's just something I happen to use. And so then just like instead of using futures directly, I use Dask PyTorch DDP, but just like futures, I hit run and it will take the Dask client and it will train the model on all of the workers, and then DDP will be communicating with them. So it's really not much overhead compared to if I was using one GPU, but because I'm using a Dask cluster, I'm now using any number of GPUs, which can be a lot faster. So I actually tested this. So I tried it with 1, 4, and 16 workers. So I had a Dask cluster with 16 workers, and I used 1, 4, or 16 at any given time. Each one had a GPU, and I used weights and biases to monitor the results. And when I did that, and I tried it with a bunch of different parameters and stuff, I basically saw, as you'd expect, that having 4 or 16 GPUs can increase the training size by 4 or 16 times. So it was actually pretty remarkable that I was able to get that kind of an improvement. And you can imagine, I mean, like training a neural network to create pet names, who cares? Like, but if you're actually doing this for research or things like this, the ability to speed up your model training by an arbitrary amount based on just how many extra GPUs you throw at it, that's like a pretty cool thing to be able to do. So given all that, in conclusion, I want to say Saturn Cloud, it's really great. If you do want to try just switching from your laptop to your cloud or a distributed cluster cloud, it's really great. Give it a try. And in particular, we're pretty good at making Dask clusters easy to use. So we're here to help you. But then more in general, just even if you don't want to use Saturn Cloud, Dask is a really nice way to parallelize Python code. So it's a really nice way to make it so that your code and data can be working on a distributed cluster rather than just your laptop. Some simple tricks: you can use Dask Delayed for taking functions and parallelizing them. You can use futures to run a bunch of things at the exact same time. Or you can use things like Dask DataFrames and Dask arrays to mimic existing data structures, but do it in a distributed way. So with that, before I open it up to questions, just a minor note that in 2 weeks, we're having another webinar by Mitali Sanwal. And she's going to be talking about using Prefect. And Prefect is a pretty cool tool for data pipelines. And so that might be something you want to catch too.